STM, Software Transactional Memory. What is it? What can we do with it? And how can we use it in our applications? If we go to Project Arrow's webpage in arrow-kt.io, we will find 6 different options that we can choose from. One of them is Quick Start, then we've got typed errors, then concurrency and resources, resilience, immutable data with objects, and collections and functions. In Quick Start, we can have a look at how Project Arrow works and how can we quickly start with it and learn how it does what it needs to do. Then we can choose typed errors, and this is a small introduction about the different patterns that we can use in Project Arrow, and it starts out with very simple patterns. Then we move on to concurrency and resources. These are more specific to Kotlin coroutines and how can we better manage our Kotlin coroutines in our code. So resilience is also an interesting one because it also uses Kotlin coroutines. And then we've got immutable data with objects. Arrow optics allows us to work and process data that is deeply nested in different data structures. And then finally, we've got collections and functions that provides extra functionality when we are working, for example, with collections that require different functions for them. But we are talking about software transactional memory, and that is located in concurrency and resources and then under transactional memory, of course. Now, transactional memory or software transactional memory is actually a generic concept that has been developed from a long time ago, actually since the 80s and 90s. And in the beginning of the 90s, there was a document that has been written, or a draft or a paper that was written by Maurice Herlihy and J. Elliott Moss called Transactional Memory Architectural Support for Lock-Free Data Structures. Think about the title, Lock-Free Data Structures. This is the main point of using software transactional memory, because the idea is that we can avoid the phenomena that can occur with using locked systems. Now, if you have been working a long time with transactional systems, especially using the database, you are used to this concept of locks. And locks always lead us to one specific problem that is called a deadlock or a race condition, which is a problem that I think many developers, maybe not all of us, maybe a small percentage of us, maybe just some people, we kind of developed this idea that this is something that we need to deal with when we are working with databases, and it always comes up when we are doing that. Well, in this case, transactional memory wants to make sure that we don't have to worry about that. But there's a difference. When we are talking about databases, we are intrinsically dependent on transactions that occur in a database. And therefore, when we couple for example, our JPA repository, our CRUD repository, or our coroutine CRUD repository, we are dealing with queries that are using the database. And some of these queries may use a transactional system. And if they are using a transactional system, they are using the isolation levels of a database. But transactional memory in this case means that we can deal and work with data and process it in memory, and only at the end commit that data and see what happens. Maybe we can persist that data in memory, or maybe not. But that is what it intends to solve. And because it's in memory, it leads to the creation of a system that is deadlock-free and race conditions-free. Now, how does this work and how is this possible? Well, the theory is enormous, and if we look at the original document that is available in Brown University, we can download the whole document and read it, we may understand how it works. But I want to sum it up to very small lines of text. Simply what this does is when we create a transactional system, something like this will happen. This is what we normally see when we are performing transactions, for example, in a database. So we've got transaction A and transaction B. Both of them are performing operations in the database, especially updates or edits or inserts. Whatever the case, when we are dealing with this, we are potentially also dealing with conflicts. And dealing with conflicts is something that if you are used to dealing with databases, especially if you are working with the Spring framework, for example, with the JPA, with the Java Persistence API, then you probably know that you need to deal with things like database isolation, you need to deal with the levels of the transaction that you want to deal with, and you also need to deal with mechanisms of pessimistic and optimistic locking. And the whole reason and the goal is always to avoid deadlocks and to avoid race conditions, but also to avoid data inconsistencies. We want to make sure that our data is consistent. But that is considering a database. STM solves a different problem, potentially can also solve database problems, but it solves memory issues. And similarly to how databases work, it also tries to avoid deadlocks and race conditions, except that in this case it avoids them completely because the mechanism is different. And how it works is kind of like this one over here. In this case, we are seeing two different transactions. One transaction makes a change to the data, and the second transaction will find that change. The first transaction will commit, and the second transaction will commit as well, but it will try to commit to a change that it didn't expect it. And in that case, what will happen is that it will automatically restart the whole transaction and perform that change for us. If it doesn't succeed on the second time, and it does not have to do with changes in the data, then of course the transaction will also stop, but in that case, there will be no more retries. You see how it works? There is no chance of deadlock because one of them will have to succeed committing before the other one can trigger the restart mechanism. So, and in other cases, we can have multiple retries like this until we get a result, until the two transactions can commit together. And in that case, we've got commits from a transaction A and commits from a transaction B. But STM is very interesting in the perspective of code. How do we implement this and how do we use it? And how do we make sure that we don't use this in a wrong way? And how does it actually work? Now, these are all interesting questions that we will try to answer in this video if we start looking at the example that I created for us. But before we make a deep dive in our example, I just want to mention one important thing. Everything that we've discussed here, the way that the transactions work and how we make sure that they avoid deadlocks and they avoid race conditions, that actually has a name. And the name is called optimistic concurrency control. And this is a strategy to deal with different transactions that exists since the 1970s, since 1979 to be more precise. This strategy can be used in these kinds of paradigms, these kinds of patterns, to make sure that we perform our transactions in this kind of way where we avoid all of these problems. Now, this works in memory, can potentially work in databases, and that's all I wanted to say before we continue to our example. So now let's go to our example and let's go and make a quick dive in what I have designed for you so that we can understand more about this. So if we go to our project, which is called Spaceship Parent, this is available on GitHub under my handler J. Esperansinge, and here we can find our example again in app. If you saw this video over here, you know where to find it, and if not, let me just tell you where it is. Basically, you just go here to main, to Kotlin, and here I've already made some changes to my service, and I have separated the DAOs from the service, and now we have in service a new service called docking service, and docking service is the example that we are going to have a look at today. So, what I've got in the docking service is something that simulates refueling of spaceships or docking of spaceships. We start out with a simple example, which is the docking bay example, and then we are going to go to the fuel station to try and fuel our spaceships. We're going to tank in these stations for our spaceships. So the first example is the docking service. Let's first have a look at what it has here. So docking service starts with two different initializations. So these two initializations are creating a docking bay and a fuel station. But if you look at this closely, it's not creating these instances in a normal way. What it's doing is creating this via tvar and new. Tvar means transactional variable. And that means that we are creating two different transactional variables that are the representation of our docking bay and our fuel station. The fuel station starts with 100 as fuel, whatever unit you want to call it. For the example, it doesn't really matter. And then the docking bay will have place for one single spaceship. Now, why are we doing late init var and not doing a simple val or simply injecting or simply creating in a different, more simpler way that Kotlin provides? Well, late init var has very specific uses, and this is one of them. The reason for this is that if you notice the way is being created. Initialize is being created using a suspend function. We are using initialize with a suspend function. Now you can say, hey, don't use a suspend function. It will be much easier. The problem with that is that new, in this case, is a suspend function. STM in Project Arrow relies heavily on coroutines. And that is not a surprise. That is exactly how it works behind it. Now, we are creating transactions in memory. We are creating memory-based transactions, and these transactions are highly dependent on coroutines. This is important to understand and keep in mind as we are going through the code. Now, okay, but how can this actually fix the problem of initialization? For this example, I am creating a service that will later be used on a controller, and we are trying to manage state. That's also another thing that STM provides, is a way to manage state in a transactional way in our application. I mean, there are many different uses for STM. And so if we need a state, and to keep that state, think about it. How would we initialize a global variable in another way by using this new? I mean, it's a suspend function, right? If I would use here val, this wouldn't work, because by using val here, I could potentially use this like this, but val, in this case, would accept incoming variables of type tvar_docking_bay, so this would compile. But the problem is that if I would then initialize these variables from here, and I would do this, this wouldn't work, because new, of course, is a suspend function, and that is not the way we initialize variables in our instances. And so I had to formulate a way to be able to use global variables that would keep state in a service. And this is the way I decided to do that with a late init var. This is relevant to our example because it has to do with how would we create a state in a service for us. And this is one way to do that. Now, important is that this docking service will be used in controllers in the future. It will be used in Ktor language in routing, but it is important for us also to understand how the services are initialized in Ktor using coin. Now, I've explained this in that video before, but important here is that we go to administration at this point, or frameworks in this case. And in frameworks, we can find all the different initializations of the different services that I have created for this whole example of spaceship parent. But the important one for us is the docking service. I want a docking service to work, but I also want the service to initialize my variables. So I implicitly call that initialize method over here by using a coroutine scope with dispatchers.io as context. This is the dispatchers that I decided to use here. We can choose any other dispatcher. It doesn't really matter at this point because this is all about the initialization of this service. And then we launch it, and then we simply just initialize a docking service over here. We initialize our variables, and then in the end, we create our single instance, our singleton, effectively, that will be able then to inject in our application by giving it the type and putting here the actual service we want to make available in the whole of our application using coin. But we are not going to inject anything here. We are simply just going to perform unit tests. But before we get to the unit tests, now we need to further continue with the example, now that we understand why we did this and what this actually is. So we've got transactional variables here, and transactional variables can only be handled under an atomically scope. Atomically in this case means exactly the transaction. We are creating a transaction with atomically, and this will simply run this example here, and it will make questions. So for example, when we read that the bay is not occupied, we can then put our spaceship. But this will happen at the same time for transaction 1 and 2. If we launch two different transactions calling this method, we'll make sure that one of them will get the bay not occupied, but the second one will probably get it that it's occupied, because look at what it does here. It will write that the docking bay is occupied. But here's the thing. They will run all the way up to here. What will happen, and we will not see this in the code very clearly, is that it will try to dock once, and it will work, the first transaction, and the second transaction will try to dock once, it will fail, and on the second time it runs, it will say, spaceship must wait, docking bay is occupied. So let's look at the unit test that calls this method and test it if it works. So if we go here to test, and go to Kotlin, and go to our test for the docking service, this one over here, at the top, we will find should succeed request docking. This is a test that will simply create a test application for us. It will load the whole module of the application. It will make everything available for us, and it will allow us to use the service that will be injected here. Yes, by inject, but not via coin. This inject is via coin test. So it's a subset of coin that allows us to make unit tests using the injection framework. So in this example, we are launching two different services. I'm calling two different spaceships here with two different names of bridges around Lisbon. There is the 25th of April bridge, and there's the Vasco da Gama bridge that we use to cross the Tagus River, or in Portuguese, Tejo. That's just a curiosity of the video. But anyways, we are launching two different spaceships that have different names. That's the point. We launch them, and we are trying to dock one of these spaceships to the port. Now, I'm not doing any assertions in this test. What I do want to see is the log. So let's now just run this and see what happens. Before we do that, important is that we realize that we are launching all of this in parallel with the dispatcher's IO context in a coroutine scope. So this is important. We'll launch them in parallel. If you are interested in learning about coroutines and you want to understand this a bit more, I sincerely advise you to have a look at my 5 different videos about coroutines, which start from here all the way up to here. This is a whole course that I'm doing about coroutines. It keeps evolving and it has more and more episodes. Make sure to watch the playlist. I will put the link in the description. Make sure to read that. So now we just want to run our test and see what happens when two spaceships try to dock in the same port. Let's see what happens. We will run this. The test should run successfully because I'm not doing any assertion, and I also don't expect any error to occur. But what it is important is that we read the logs and understand a very basic principle around here. We are saying that Vasco da Gama is docking, 25th of April is docking. Now, the two spaceships are trying to dock at the same time. It says that the two of them docked successfully, but the 25th of April must wait because the docking bay is occupied. What happened here is that both of them tried to dock. Let's put this in parallel so that we can understand this more clearly. If I go now to the docking service and look at the example, we can see that, all right, so in this case, Vasco da Gama docked successfully. This one is the first one that was able to dock to write that our docking bay is occupied. Now, because it didn't commit it yet, 25th of April also says, hey, it successfully docked. But the problem is that the commit occurs right here at the end, here, when we leave the scope of the atomically. When we leave that scope, both of them will try to commit. And what happens is that the first successful one will be the winner, and the other one will lose. And when it loses, it will try again. And when it tries again, it will see that, hey, it is occupied. So that means that it will print spaceship must wait, docking bay is occupied. And that's what we see here. 25th of April must wait, docking bay is occupied. So this is a basic example that tells us what is going on in this case when we are trying to run two different transactions on the same target when we are reading from an object. Here we are just using a simple instance of an object that is running in our application, and we are with the tvar measuring changes that are occurring to it. Essentially, in this case, we are just essentially seeing if it has been replaced or not. So the docking bay, has it been replaced? Has it not been replaced? And if it has, then the other transaction will know and fail if a change has occurred and he tries to commit to the same target. So this is the first example. The second example is refuel. Now refuel, let me just put it in the whole screen so that we can have a look at what it is more exactly. we still have the atomically here, and we are here running one transaction. So every time we call this method, we are calling a transaction that will operate on the fuel station object. This one over here that we saw at the top, and it's now a tvar fuel station. So this generic type is now a tvar fuel station. Now, the first thing it does, it reads the fuel station, and then if there is enough fuel, then it will refuel the ship. And it will try to write and update the fuel station. And then it will say, spaceship has been successfully refueled. If not, then the spaceship will fail. Then it will not be able to refuel. So this is a simple example, which is essentially some repetition of what we saw before. Let's have a look at what happens when we run the test. So if we run this test, which is this one over here, just very quickly, we are refueling in the same way as we did before, but we are refueling with the first spaceship 25th of April with 50, and then we are refueling Vasco da Gama with 100. Now, both of these cases can be successful because we are launching them in parallel, and that means that when I'm making this assertion over here to find out how much fuel is left on the spaceship, I want to know if it's 0 or 50. Anything other will be a failure, because if Vasco da Gama is the first one, then that means that all the fuel will be taken out of the fuel station, and if not, then only 50 will be taken out, and we will get 50 in the end. So let's see what happens in our logs, because this will run also successfully, but we will be able to see the behavior in our logs. So when we have a look at here further down the line, we see that the 25th of April spaceship or bridge is refueling with 50 units, and Vasco da Gama is refueling with 100 units. They all try at the same time. Now, 25th of April successfully refueled, remaining fuel 50. Vasco da Gama successfully refueled, remaining fuel 0. Of course, this is before the commit, so we get all the different logs as if the two spaceships were successful, except that when the commit occurs, the first one to commit in this case was the 25th of April, and that means that Vasco da Gama will have detected this error and will try to run the transaction, and upon the first retry it will find out that there is no longer fuel available and it will fail. Now, these logs are here only for tests. This is not something that you should do in production. This is just simply a way that we have to visualize what is happening in the background. And remember that these two different calls to our method in our service, the refuel, will have been made in parallel in this way with a coroutine scope using context dispatchers.io. And if you want to learn more about dispatchers.io, there is this old video that I did a while ago that explains really well what dispatchers.io are and how they can be used. This is just a response to a quiz. I sincerely advise you to watch the quiz and watch the answer to the quiz that I give in this video, because it is something that if you are not very used to using coroutine scopes and coroutine contexts, then perhaps the video will help you better understand how they work. But in any case, let's have a look at the last example of this video, and the last example of this video is called refuelWithRollback. refuelWithRollback is an interesting one, because if we go here inside of it, we will get the same method as before, the refuel, except that right now I am simulating a failure. And this is what I've mentioned before. If there is no conflict and there is still an error, then that means that the commit does not occur. And that seems logic, but that's something that we want to see if it actually works that way. And so what we are going to do is, if we are requesting fuel of 20, then it will fail. Now, this is just an implicit way of creating an error. We're just simulating an error. It doesn't mean that it has to be 20. It's just a way of throwing an illegal state exception and then just saying spaceship encountered a system failure. All right, so let's see what this does. It then continues to say spaceship successfully refueled, remaining fuel something something, which is the fuel of the spaceship, and the same thing, if it fails, then it cannot refuel. Now, if there's a failure here, and our test looks like this, and we've got over here start of atomic transaction, now here's an exercise for you. How many times do you think we will see that log line start of atomic transaction in our logs. What is the likely number of times that we are going to see that start of atomic transaction in our logs? So let's see, we are launching one coroutine that will call refuelWithRollback from spaceship 25th of April. At this point, you already notice that the name doesn't really matter for these algorithms. But what does matter is the requested fuel with 50. So it will take 50 out of the remaining fuel. There's another one which will take 100. And there's another one that will take 50. In this case, no error is going to be thrown. There will be no failure. And this will be successful, and I'm saying here that the fuel should be 0. The reason for this is that whatever combination we decide to do here, the result of the fuel will always be 0, because if this one is successful, this one will fail and this one will be successful, which means that 50 and 50 is 100 will be 0. If this one is successful, it will be immediately 0 and these two will fail. And if this one is successful, then we could have this one as a success or this one as a success, but this one will definitely fail and this one will be successful, making a collection of 50 plus 50, and that will be 100 as well, which will take all the fuel out of the fuel station. But important, how many times do you think that log is going to appear? So in all of these cases, we found that at least one fails, and there could be two that fail if this one is the first one to go in. And if two of them can fail, then that means that both of them will try to perform again the transaction. So that's now 1, 2, 3 plus 2, that's 5. If this one is successful, and this one fails, then we will have two successes, one that restarts, so that means that we've got 3 already, but one that restarts, so that means a total of 4. Let's see if we get 5 or 4, or something else. If we check our logs, we will see 1, 2, 3, 4, 5, 6. So how do we get 6? Let's have a look at the logs. So this one was successfully refueled, this one successfully refueled, and this one successfully refueled. So that means all 3 of them did the operation correctly in the transaction. And then what's going to happen is that 25th of April, attempting to refuel, this one has been successfully, so that means there has already been a retry here. And then the other one failed. Vasco da Gama failed, Vasco da Gama failed. The reason for this is that what we missed is that when we are making this test over here, this one was successful. This one tried to run, it failed, it tries again. This one was successful. This one tried to run and fails again. And then it will retry, and only then it will definitely fail, because then there are no changes anymore to our memory. So that means that we've got here, for this one specifically, 2 extra ones. Then we have 3, just the normal of running. And then we also have this one, which of course, when trying to change the state of our fuel station, it found that there has been changes occurred in the database, and so it ran again. So that means that you get 6 different logs of start of atomic transaction. Now for this example, let me just fix one thing here so that we can read this better. Okay, so then we can see this in different lines. For the last example. Now the last example, the last of the last, I know I said that that one was the last example, but that was not the last example. The last example is this one over here, where we are going to test the exception that we want to throw when everything fails. Now here is an important thing. When we run this, we are also running in parallel. There will be now a failure, And now I want to ask you, how many times do you think we are going to see that log that says start of atomic transaction? Let's run this test and see what happens. If we go further down in the logs, we will see that only 2 of them have occurred, but it's still 2. So what happened with these 2 different logs? It means that this refuel with rollback has been called 2 times. The transaction inside of it has been called 2 times. So this only appeared 2 times. How can that be? It's very simple. The first one was successful, so we took 30 out of the total fuel, and the second one requested 20, but we know that in our simulation 20 means an exception. It means an illegal state exception. Spaceship encountered a system failure. And so in that case, when we finally get to the end of this runtime, we will get 70 and we will only get 2 logs, because an exception means that the transaction gets immediately terminated. And so this is only a small bit on how can we use STM in our code with Project Arrow and in Kotlin. But there are a lot more things that we can do with Project Arrow. If we go here to the web page of Transactional Memory in STM, then we can find a lot of different text explaining even an example with, in this case, bank accounts, and it will tell us how to use this in different ways. Now, to be able to have used this in Ktor, as we have seen just now, I had to explore a lot and see how this works. Now, there are other examples that I really want to do in a next video, and these are other types that we can use that are transactionally safe and that we can use in atomically, and we will do that in a coming video. But it's important that we understand that the other types that we have that are available for us are this one, TQ, TMVAR, TSET, TMAP, TArray, and TSemaphore. How are they useful for us? We will see later. It's not important for now. What's important for now is that we understand that STM is a way that we have at our disposal that works in a different way that transactions work in Spring, even if we don't use them with databases, which, surprise, if you didn't know, now you know, that we can use those transactions also for in-memory entities. But here we use this in a completely independent way and in the form of a library. Not a whole framework, but a library, which can be very handy if we are using alternative things to Spring, like for example Ktor or other kinds of frameworks. It is completely independent and you can use it as well in a simple Java application. You don't need to inject it. You can just simply do something with it. You can do it in Kotlin and then you can compile it to run as a Java application. Don't confuse when I say Java application with Java code. Remember that everything that we compile in Kotlin is still Java. We still run a jar and we still run it in the JVM, the Java virtual machine. All right, so this was the video about software transactional memory. I thought this was important that we have a discussion about this. These are things that have been developed through the years. They start out in 1979 with the optimistic concurrency control. And then at the end of the 1980s, begin 1990s, we've got different scholars that then start implementing the first strategies and philosophies around software transactional memory. If you enjoyed this video, make sure to give us a like. Make sure to subscribe to this channel because I'm posting a lot of new videos in the coming period. And make sure that you read the description so that you get well informed about the topics that we discussed here in this video, and perhaps even read the different documents that I will post the links there also for you to read if you are interested and if you have the time for it and the patience for it, of course, because those are big essays and big abstracts. And make sure to leave a comment. I really appreciate the comments to my videos. I always try to answer back and reply and react to them and make sure that we establish a community, a Just Protect community. And until the next video, Be sure to stay tech, keep programming, be kind, and have a good one. Bye. As a short disclaimer, I'd like to mention that I'm not associated or affiliated with any of the brands eventually shown, displayed, or mentioned in this video.